Hey, welcome to The Explainer. When you think about good code, what's the first thing that comes to mind? Speed, right? How fast it runs. But what if I told you there's another, equally important piece of the puzzle that often gets ignored? That's right, we're talking about memory. Today, we're diving into space complexity, figuring out how much memory your code really needs to get the job done. All right, let's just get right to it. The question that's probably on your mind, come on, our computers have tons of memory, right? Memory is cheap, storage is everywhere. So why on earth should you care about optimizing for every little bit of it? It's a really good question. So why should you care? Let's find out.
Well, the classic textbook on algorithms has the perfect line for this. As you can see, memory might be cheap, but it is definitely not free. Just think about it. The apps on your phone, the code running in your car, even something as simple as a smart thermostat. In those situations, or when you're dealing with absolutely massive data sets, using memory efficiently is everything. It's literally the difference between an app that's super snappy and one that just crashes.
Okay, so what are we really talking about when we say space complexity? It's a bit more than just the variables you declare. Let's break down how a program actually eats up memory. So at the most basic level, space complexity is just the total amount of memory an algorithm needs to run from start to finish. Now, this includes the obvious stuff, right? Like the space for your inputs. But here's the kicker, the part people often forget. It also includes any extra temporary space your algorithm needs while it's doing its thing. And this formula right here, this is pretty much the key to the whole thing. Just think of it like this. The total space, S of P, is just made up of two parts. You've got C, which is the fixed constant part. This is the memory your program needs just to start up, no matter what you feed it. But SP, that's the fun part. That's the variable space. It grows, it shrinks, all depending on the size of your input. And honestly, that's the part we, as developers, spend most of our time trying to make better. So you can basically think of a program's memory as being in three different buckets. You have the instruction space for the compiled code itself. Then there's the environment stack, which juggles function calls. But for what we're talking about today, we're going to zero in on the data space. Why? Because that's where all your variables and data structures live. It's the part you have the most direct control over as a programmer. All right, that's enough theory for now. The best way to really get this stuff is to see it in action, right? So let's walk through a super simple code example and break down its space complexity step by step. Okay, so take a look at this function. All it does is take an array of numbers and add them all up. Super simple, right? But let's put on our space complexity hats for a second and ask the real question. How much memory does this little bit of code actually use? Okay, first things first, let's hunt for the constant space. Remember, this is the memory that stays the same no matter how big that input array is. So we've got n, which stores the size, we have I, our little loop counter, and s, which holds our running total. Each one of these just takes up one fixed little slot of memory. So add them up, and our total constant space is 3 units. Easy. All right, now for the part that changes, the variable space. See, the space for the array A itself, that's not fixed at all. If you pass in an array with 10 numbers, it's going to need space for 10 numbers. If you pass in 1,000,000, you guessed it, it needs space for 1,000,000. The memory it uses is tied directly to the input size n. Okay, so let's put it all together. The total space needed is our variable part n plus our constant part 3. But here's the thing about complexity analysis. We're not too worried about small inputs. We care about what happens when the input gets huge. If n is 1,000,000,000, does adding 3 really matter? Not so much. And that's exactly why we simplify this whole thing down to big O of n, or O of n. It just means the memory usage grows in a straight line, right along with the input. All right, so we've tackled a simple case. We get it. Now, let's zoom out a bit and see how this fits into the grand scheme of things, because you never really think about space complexity all by itself. It's always, and I mean always, part of a classic balancing act in programming. So whenever you're designing an algorithm, you're constantly juggling these two big questions. How fast is it? That's your time complexity. And how much memory does it need? That's your space complexity. And the really tricky part? They're often like a seesaw. If you push one down to make it better, the other one often goes up. This is that famous space-time trade-off you hear. And here's a fantastic real-world example from the world of graph algorithms. The standard version of the Floyd-Warshall algorithm, its space needs grow cubically. That's n to the power of 3. But some smart folks figured out a modified version that only needs n squared space. Now, Going from n cubed to n squared might not sound like a game changer, but trust me, if your graph has thousands or even millions of nodes, the difference is absolutely massive. It's a huge memory saving that can take a problem from being totally impossible to solve on your computer to something that's actually doable.
Which brings us back to the fundamental question that every single developer has to face at some point. Do you chew up more memory to make your program run faster? Or do you save that precious space, even if it means things take a little longer? And the most important takeaway here is this. There is no one-size-fits-all answer. It always depends on the context. Are you writing code for a beast of a server with tons of RAM, or for a tiny little sensor on a shoestring memory budget? See, understanding space complexity isn't about memorizing which algorithm is best. It's about having the tools and the knowledge to choose the right solution for the problem you're trying to solve.